Okay, is everyone submit the paper? Okay. Okay. So those are very simple question, and then so what is the answer of A? One A. The number of architectural general registers. There is by microarchitecture. So in this example, the Intel Celeron and Intel Core series use the same x86, then the number of architectural registers can vary. No. So the answer is false. So it is because, so actually in this course, so we learned that the number of architectural registers, the number of actually general purpose registers is defined in ISA document, right? So I mentioned that for RISC-V, the number of general purpose integer register is 32, right? So it is defined in ISA, not microarchitecture. The number of architectural registers is the same if the processors use the same ISA. And how about B? It's true, right? So only memory instructions, such as load and store instructions, can access memory, right? And then other instructions cannot access memory, right? How about C? It's 32, right? No, 64, because it's the RISC-V 64-bit ISA. So the width of single register, general purpose register is 64-bit, okay? But we are learning about the 32-bit RISC-V ISA. So which means that the width of 32-bit ISA is also 32-bit. And it's simple, so we can use add instruction and add I instruction, right? Okay, so just the package. Okay. So actually, in the today's class, I hope we can conclude the chapter 2, the instructions of RISC-V. Okay. So in the previous class, we learned about the pseudo instruction, and then I mentioned that this pseudo instruction is just fake instruction, right? The pseudo instructions are the fake instructions, and then we can make pseudo instructions using the existing instructions. So these are examples. So we can use RAT, it means return, but RAT is actually R0, RA0, right? And then also label. The label just represent the target of branch instruction, and then it represents program counter, right? So, and then we also learned about the arrays and then some other stuffs. And then, so in the previous class, we learned how to generate machine languages from RISC-V assembly instructions. And then there are actually 4 types here. And then based on the instruction format, and we can generate the machine code. Okay, so these are examples. Actually, in the previous class, we learned about the R-type instructions. So R-type instruction is that the instruction requires 3 register operands, right? So RS1 and RS2. So an instruction requires 2 source registers. Okay. 2 source registers and 1 destination register. Okay. Okay, so this time, so and then we will learn how to make I-type machine code. So in this slide, so I-type. So it's an I type. So I represent immediate type. So what are immediate numbers? It's small. So immediate numbers are small constant numbers. And then, so we learned about the immediate instruction such as add I. Okay. So I type instructions use one immediate type operand, and then is the width of this immediate number is 12 bit. So then we also remember that the immediate number for I type instruction is 12 bit 2's complement number. So which means it's signed number. Okay, it's a 2's complement number. So and then this so for example add I requires the one source register and immediate number. And then this immediate number is the 12-bit signed number and one destination register. So and then immediate type data. So you mean I type instruction. So actually have the same format. So for example, some other instructions like or I. So or I also has the RD, RS1, and immediate. So format is the same. So it's similar to R-type instruction. So R-type instructions also have the same format. It's also same to the I-type. So I-type instructions such as add I or I. So you can find the I here. It means the immediate. And then these instructions have the same format. Okay. So this is the format of I-type machine code, machine instruction. So actually, so we need to use the 12-bit immediate number. And then I mentioned that the size of a single instruction is 32-bit. So compared to the R-type instruction, actually R-type instruction use the two source registers. And then we can represent the number of the register number as the using 5 bits. But you know, for the immediate type data, we need to use the 12 bit. So it's longer than the register number. So that actually, so we can just use 5 bits for representing register number, but immediate field need to occupy more bits. So for the I-type instruction, the immediate number occupies the upper 12 bit of instruction. So bit number 31 to bit number 20. Okay. And then there is RS1 field, and RS1 field also occupies 5 bits. So it's a register number. And then RD is here, the same position. And then OP code is here, and then function 3 here. So using the OP code and then function 3, that we can identify instructions. And it's the same, right? For the R-type instruction, you can also identify instruction using OP code function 3 and then function 7. But for the I-type instruction, upper 12 bit is used for immediate number. So we cannot use the function 7 field. But instead, we can use OP code and function 3 field to identify instructions. Okay. So we can observe that. So this is the RD field. This is the RS1 field, and then we can observe that the position of RD field and the RS1 field of R-type instruction is the same to the positions of RD and RS1 of I-type instruction. Actually, the same position. So it's a then the first rule of the instruction, the ISA, is the simplicity favors regularity. Okay. So which means that in this example, I type and R-type instructions use the same positions for RD and RS1. So it's the same in regular. Then if the regular format is used, then we can design simpler hardware. Okay. So this is the I-type instruction. And then let's see the example. So in this example, you can find the add I as 0, as 1, and 12. It's an immediate number. 12 is the immediate number. And then this ABI name of register actually needs to be represented as using register number. So S0 is the actually X8, and then S1 is the X9. So we need to use this number for representing register operand, right? So in this example, immediate number is 12. So 12 occupies the upper 12 bit, and then RS1 is 9, okay, because it's 9, and then RD 8, and then OP code is 19. It's in, and then this represents the immediate type instruction. Actually, immediate type arithmetic and logical instructions. Okay. So, and then 0 represents the add I. So, it's just simple. So 12 is we can represent 12 using binary number like this, and then 9 is the 0, 1, 0, 0, 1. Then the function 3 code for add I is 0, so 0, 0, 0, ID 8, like this. So we can, based on the encoding rule, we can generate the machine code for this add I instruction. Then another example is, so in this is another example, this is another example. So you can find the immediate number is minus number, it's a negative number. And then we learned that immediate number is the 2's complement number. So which means that this immediate field needs to be represented using 2's complement negative number. Okay. So that's why minus 14 is the 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0. Okay. And then also load word. Load instructions also use the I-type format. Okay, because if we see the load instruction, it's a load word, and then RD, it's a one destination register, and offset. So offset is the 12-bit immediate number, and RS1 source register. So load instructions also require one source register, one destination register, and one immediate. So load instructions also use the I-type format. So, but the OP code is different. So then OP code for load instructions is 3. Okay. So we can find that for the load H and LH and LB also use the same OP code 3 here. And then using the same rule, then we can build up each field of this machine code, machine instruction. So in this example, immediate number is -6, it's -6, and then 19 is the source register, okay, and then 7 is the destination register number, okay, and then using the function 3, then we can identify load word, and then load H, load head word, and then load byte. So load byte is 0, and then load head word is 1, and the load word is 2. We can generate the machine code like this. So I-type instruction. So arithmetic and logical I-type instruction and load instructions use the I-type format for generating machine code. Okay? And then The third type is the S and P type instructions. So actually, the S represent the store and B represent the branch, conditional branch. Okay, so conditional branch. So what are characteristics of these instructions? Why? So the S type, so it's a store type, and then B type, the conditional branch. Store requires two source registers, right? Because stores read data from register, and then also store instruction needs to calculate the target address using the base address stored in the another source register. So store instructions require the two source registers. Conditional branch is the same. So conditional branch is just compare the data in two source registers. So conditional branch instructions require also two source registers. And for instruction requires immediate number. So you can use this immediate number as the offset of base address. And then branch is the same. Branch also has the immediate number. So this is the offset from the current PC program counter. Okay. So store instruction and branch instructions, the both instruction type use two source registers and then one immediate number. So this type of instruction is called the S and P type instructions. But the format is slightly different. Okay, so you can find the RS1 is here and the RS2 is here. So because of these instructions use two source registers, so you can find the RS1 and RS2 here. Because it's here and function is here. And then you can use the immediate field like this. But it's a little bit different from the I-type instruction. If you see the IS time, the position of the immediate number is different. Also, for the B type, immediate number is differently assigned to the 7 bits and then 5 bits here. Okay, so I will explain the reason later. So just remember that S and P type instructions use two source registers and one immediate, and then immediate field is allocated like this. But S type and P type is different for the positions of immediate number. Okay, let's see the example. So S type instruction, it's a store type instruction. So it's a store type. So it requires the three operand RS1, RS2, and immediate. Immediate is the 12-bit 2's complement. It's the same. Okay. And then store type instructions use RS1 as the base register. So which means that it is the base address. Okay. And then store instruction reads data from RS2. Okay. This data is stored in memory. So RS2 is the value to be stored to memory. And then we can use the other field as the OP code and function 3. And then, as you can see, immediate number is allocated like this. So it's a little bit different, right? For the I-type instruction, immediate number occupies the upper 12-bit field. But S-type it's different. Why? Because so S-type requires the RS1 and RS2. So these bits are assigned to the RS2. So the lower part of immediate number actually allocate to the RD position, right? ID position of the I type or I type instructions. We just for the RISC-V, the position of RD and RS1 and RS2 is usually the same. Usually. So it's an example. So T2 is the X7, and then also you can find the offset here. So -6, it's immediate number. So -6 is the 1111, 1111, 1010, right? So I mentioned that pin number 11 down 5 is allocated to the upper 7-bit field of the immediate field. So 111111. So these bits are allocated to this position. Okay. And then lower 5 bits 11010 is allocated to this field. Okay, and then RS1 and RS1 and RS2, the positions of RS1 and RS2 are the same. Okay, and then for the store instruction, we use the OP code 35, and then using the function 3, we can identify word, half word, and byte. Okay, so this is the example of S-type instruction. And then branch. Branch is actually the branch also use branch instruction. It's a conditional branch. Conditional branch. Branch instructions also use 3 of 1, RS1, RS2, and immediate. So it's the 12-bit two's complement. It's the same. But you can find the different bit numbers. So for the S-type instruction, immediate field is just IMM. So this immediate field actually represents the immediate level down to 0, right? But for the B-type instruction, the immediate field represents the 12 down to 1. Why? So if we see the branch instruction like BQ, so we can RS1, RS2, and immediate. Okay. Actually, this is the target of the branch, right? And then we can calculate the target of the branch, like the target is the current PC, the PC of the branch instruction plus immediate number, right? So, but we just use the upper, so we just drop the 0 bit for the branch instruction, then we just use the bit number 12 to 1, right? Right? So it is because this immediate number should be power of 2. No. Multiple of 2. Multiple of 2. 이해되죠? Multiple of 2. Okay? So that means that it's even number. So for the even number, the LSB is always 0, right? Because this is the even number, and then we use the binary number. So LSB of even number is always 0. So actually, we don't need to store this information in the instruction because it is always 0. So for the branch instruction, because the immediate number is always multiple of 2, we just use so for making the machine code, branch instruction just use the pin number 12 to 1 for the immediate number. So it's different from the S-type instruction. And then you need to remember this. So sometimes it's confusing, right? Because the store instruction and then branch instruction both use the two source registers and the one immediate. But the immediate field is differently allocated to this immediate field. Okay? And then also it's little bit weird. So when the immediate number is assigned to the immediate field, so as you can see, the bit 12 is assigned first, and then bit number 10 down to 5 is assigned to the upper 7 bit of the immediate field, and then bit number 4 down to 1 is assigned to the lower 5 bit immediate field, and then 11 bit is assigned. So it's a little bit weird, right? Okay, so let's see the example. So this is the immediate, it's the example. So in this example, the BQ, the target of BQ is L1. And then where is the L1? L1 is here. So, and then if we see the PC of the disinfection, the PC of BQ is 70, and then 74, 78, 76, 76. So what is the difference between this PC, it's a 70, and then target? The difference is 0x is 0x10, right? It's 16 in decimal number. So actually, in this example, the L1 is actually 16. This is the immediate number, right? Do you understand? Because so we can calculate the target of the branch like the PC is 0x70, so it's the current PC, and then target is L1. L1 is here. So PC is 0x70, it's PC, and then plus immediate number is 16. So this is the 10 in hexadecimal number. So this is the 0x80, the target of branch instruction. Right. So actually the immediate number is 16. So and then if we represent this 16 into binary number, then this should be 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, right? Right? It's 12 down to 0. So, okay. But when this immediate number is allocated to the machine instruction field, then we just wrap RISC-V of the immediate number, and then we use the pin number 12 down to pin number 1. So these bits are assigned to the immediate field of B-type instruction, the branch instruction. And then these instructions are located, but the encoding rule is somewhat weird. So 11, this is the 11th bit, right? So this bit is assigned first here, right? And then 4 down to 1. What is the 4 down to 1? Well, this here. So this is 4 down to 1. Okay. 4 down to 1. So these bits are assigned here. So it's not weird, right? And then, so when the upper 7 bit is allocated, Pin number 10 down to 5 is assigned here. Okay, then pin number 12 is assigned. So yeah, so actually the immediate field of the branch instruction is it's a little bit weird, okay? But it's just the rule, okay? So then we need to follow the rules defined in ISA document, okay? Actually, this rule is designed for hardware implementation, okay? So this is the bit type instruction. And then finally, there is U and J type instruction. So U type instruction represents the upper immediate type. So for example, LUI. So we learn the LUI. Also, jump instruction. Jump instruction also use the J type format. So these instructions, so LUI and then jump instruction, just to use the 20-bit immediate number. So this immediate number is the 2's complement number and one destination register. Okay. So UNJ type instruction use one destination register and one 20-bit immediate number. Also, so this is the format of the U type and J type. But as you can see, the immediate number is differently assigned to this 20-bit immediate field for the J type. Okay, also it used so actually the RISC-V is also dropped, right? Jump is also calculate the target, like the target is the PC plus immediate, and then this immediate number is the multiple of 2. So even number. So we just drop the RISC-V for this immediate. So let's see the example. So for the U type instruction, then which we learn the LUI. So what is the LUI? The LUI is store the 20-bit immediate number to the upper 20-bit of destination register, right? So we can use the 20-bit immediate number, but this immediate number occupies the upper 20-bit of the register, 32-bit register, right? So actually LUI requires the destination register, and then it's 20-bit immediate, so it's 31 down to 12 is stored in the 31 down to 12 of the address, 31 down to 12 of the instruction field. Okay, this is the instruction. So immediate number is just stored in the upper 20-bit of the instruction. Okay. So this is the example. So the example is the LUI, S5, and then this immediate number. So S5 is the X21. So ID is 21. And then immediate number is 20-bit immediate number can be assigned to the immediate field directly like this. So we can represent this instruction machine code like this. Okay, it's simple, right? So jump use the also 20-bit immediate number, but it used the pin number 20 down to pin number 1. So the RISC-V is blocked because immediate number of jump is the multiple of 2. So, and then as I mentioned, the RISC-V is always 1, always 0. It's always 0, right? So you don't need to store this number because it's always 0. And then actually, so every bit is very precious in instruction. we cannot waste the bit field of the instruction. So if the data is already zero, then we don't need to store this zero. So for the J-type instruction, immediate 12-bit immediate number is assigned to the upper 20-bit of instruction. But it's also the allocation rule is also a little bit weird. Okay. So this is also example. So the function 1 is here. So this function 1 is the target of the jump instruction, and then we can calculate the target of this jump instruction like this. PC of jump instruction is 0x5440C, and then plus immediate number. Okay, so immediate number is here. So immediate number is 0xA67F8. Okay, so immediate number is A67F8, and then we can calculate the target piece of the jump instruction. So this is the pin number 22, 0. Okay, is a pin number. Pin number 20 down to 0 of this immediate number. Okay. So actually, I said that these bits are weirdly allocated to the immediate field like this. So 19 down to 12, 19 down to 12 is firstly assigned, and then 11. Pin number 11 is assigned here, and then pin number 10 down to 1 is assigned, and then pin number 20 is assigned. That's a little bit weird, right? So it's a rule, okay? So this is the J-type instruction. So this slide summarizes the instruction types of the RISC-V instruction. We learned about the R-type instruction and I-type, SMP type, and then U and J-type instructions. And then as you can see, for these instruction format, the lower 7-bit field is used for OP code. Okay, the same. So actually, it's very regularly assigned to the instruction. And then the next 5-bit field is used for usually RD, and if the RD is not used by instruction, then it is allocated to the immediate, the part of immediate. And then next 3-bit field is usually used as the functions 3 field, and then 5-bit RS1, and next 5-bit is the RS2, and then we can use the function 7, or the upper 7-bit can be used as the immediate number. So for the RISC-V, the instruction formats are very regular. Okay, so each field usually assigned for same field, okay, like the OP code, or RD, or RS1, or RS2. Okay. So sometimes good design demands good compromises. Okay. So because sometimes the rules can be different, so actually, so we can just apply some different format for the different instruction types. Okay. But keep formats as similar as possible. So I said that the RISC-V is a rather clean instruction, right? Because so as you can see, so we learned about several tens of RISC-V instructions, but we can just use these 6 instruction formats for converting assembly instruction to machine code of RISC-V. And then we can just use the same rule for assigning of different fields. Okay, if format as similar as possible, and then what is the benefit? We can design simpler hardware. Okay. Then so instructions. So these instructions like add x1, x2, x3, or add I, x3, x4, and 5. Some other instruction, load word and store word. So actually these instructions are encoded to the machine instruction or machine code. Okay, like 10001111. So it's a binary data. Actually, computer can only understand the binary data. So this binary data is given to the processor. Then, in order to execute given instruction, then the processor needs to decode the machine instruction. So I mentioned that when an instruction is translated into machine code, I used the terminology encode, right? And then the machine code is analyzed or interpreted, and I use the terminology decode. So decode means that from the encoded data, the processor needs to interpret the encoded data or encoded machine code. And then this process is called decode. Decode what? Decoding. Decode is the verb. So we can say it's a decode. Okay. So in order to interpret machine code inside of a processor, the processor needs to decode machine code. Okay, it is required. Okay, so actually the processor just received the ones and zeros. Okay, and then so in order to execute instruction, then processor needs to interpret. Okay, need to understand which instruction is given, and then so how the processor decode the machine code. The processor can decode machine code based on this encoding rule or instruction formats. Okay, so as you can see, this is the summarized encoding rule. Okay, so the processor, if the firstly check the OP code field, and then if a processor check the OP code field, then processor can know which type of instruction is given. Okay, the firstly check the OP code field, then the processor can know the type of instruction like the load or arithmetic immediate or arithmetic instructions like that. So the processor can know the type of instruction like I type, and S type, blah blah blah. Then if a processor can know this type of instruction, then processor can decode the additional field. Right. If we know, oh, this instruction is the alpha instruction, then the processor reads the first 5 bits, this 5 bits, and then processor can decode the destination register, right? And then by decoding function 3 and then function 7, then the processor can know the instruction like the add, sub, multiply, one, and or instruction. And then by decoding that 5 bits, then the processor can know the source registers. So actually, based on the encoding rule, and then inversely, the processor inversely decode the given instruction, right? Do you understand? So encoder is the inverse process of the encoding. And then in order to understand, in order to interpret the given binary data, then processor needs to decode the machine code. Okay? This is the example. It's a hexadecimal code, hexadecimal number, and then this is the binary data. It is. Firstly, we check the OP code first, and this is the 51. It is the R-type arithmetic instruction. Then, then we can know, this is the R-type. Then we just check the RD and RS1, RS2. And then by checking the function 3 and then function 7 field, you can know, this is the sub instruction. Okay? And this is the, and then as you can see, this is the different example. The OP code is here. This is the I type. Okay? And then you can get the ID, and then where is the RS1? RS1 is here, and then immediate number here. So this is another example. So I summarized the RISC-V instructions here. So you can find the different category of instructions. The load type and then store type and shift type are logical here. And then if you see the load type, then load type use the high format, as I mentioned, and then OP code is like here. So if OP code is 000011, then it represents load instruction. It means, this instruction is load instruction, and then load instruction uses I-type format. Okay, and then if OP code is 10100011, this is store type. Okay. Also, you can find the function 3 field here. So using the function 3 field, we can identify LB, LH, LW, then LB, LBU, etc. Okay. And how about the shift, arithmetic, and logical? So these instructions, and shift instruction, arithmetic, and logical instruction can be used as the R-type instruction and I-type. Right. Add something like add and add I. Right? So actually it's the same arithmetic, but add and add I use the different OP code, because I mentioned that a processor firstly check the OP code field, then by checking the OP code field, we can get the also each type of instruction is given. And then R-type and I-type are different, right? So not because of different format, and processor firstly distinguishing different is processor needs to identify which interpret which type which format is used. So that's why it's the same arithmetic instruction add and add I, but the OP code is different. Okay. And then as you can see, shift, arithmetic, and logical instruction, also compare instruction. If we use R-type format, then OP codes are the same. So if the OP code is 0110011, then it's the R-type instructions of shift, arithmetic, logical, or compare. And then OP code field is 0010011, and it means this is the I-type instruction of shift, arithmetic, logical, or compare. Okay, branch OP code is here. Okay, and a jump OP code is here. So by checking the OP code first, then we can get the format of instruction, and then after that we can identify instructions using function 3 and then function 7 and here. So this is the some encoding and decoding rule of the RISC-V instructions. And then this is the summary of address mode. So actually it shows which type of data is used by instructions. So we can use the immediate type data, we can use the data stored in register. Also, we can use the data in memory, and then we can calculate the target of jump instruction. So it's a piece relative addressing. Okay, so I copied this table from the textbook here. Okay, so this is the end of RISC-V instruction. So this is the end of chapter 2, finally. And then, so I will not explain about the x86 instructions because the x86 is the CISC type, even though the most computers use x86 processors. So it means the most laptop or desktop computer, also server computers use CISC type, so x86 instructions. But x86 ISA is the CISC type ISA, so it's much more complex than RISC type instruction or RISC-V. RISC-V it's very clean, okay, compared to the x86. So because the x86 has the very long history, okay, it developed from 1974, and then actually new instructions are added and again. So that's why the instructions are now it's very dirty. Okay. Also, as you can see, so this is the x86 registers. Okay, but the register size is also different. So if you are familiar, if you are interested, then you can search for the some x86 assembly code. And you can find the registers like this. But as you can see, the register size is different. Okay? And then also, as I mentioned, the x86, like this instruction, the arithmetic instructions can also access memory. So for the RISC type instruction, the memory space can be only accessed by memory instruction. But the CISC is different. The arithmetic instruction can access memory directly. Also, the size of instruction is different. So for the RISC-V, the size of instruction is 32 bit usually. Then for the compressed instruction, the size of a compressed instruction is 16 bit. But as you can see, x86 has their x86 instructions have various length. Oh, it's very complex. Okay. So this is if you are interested, then you can read the textbook. Okay, for the x86 ISA. So this is the end of the chapter 2, and we learned about the RISC-V instructions. Okay, and then these are some design principles of RISC-V. So simplest behaviors, regularity, and then smaller is faster. It's a very important rule in computer systems. And then good design demands good compromises. Okay. And so this is the end of chapter 2, and then we are going to the chapter 3. Okay. So until the chapter 2, in chapter 1, we learned about the various layers of computer systems. And then I mentioned that computer architecture is some interfaces between software layer and hardware layer. But until the chapter 2, we learned about the ISA, the instruction set architecture. But the most part of chapter 2 is related to the software, right? Even though this is the very low level software, but instructions are just part of software. So which means that our high-level language code is compiled. So high-level language code is software, and it's compiled, and then assembly instructions are generated. So these are also software. And then from this assembly instruction, machine codes are generated. Still, it's software, right? And then machine code is given to the hardware, and then hardware execute the machine instructions. So from chapter 3, we are going to the hardware part of computer systems. The hardware part of processor. Okay, so now we are going to the hardware part. And then firstly, we will learn about the arithmetic used by computers. Well, it's very simple. And then if you took the logic design course, actually you already learned about the arithmetic operations, like add, sum, multiply, and divide, right? So in this chapter, so we will learn about some arithmetic operations in computer system. So addition and subtraction. It's very simple. So you know the addition is very simple, right? So and then computer use the binary number, and then actually we can just perform addition for each digit of binary number. Actually, same for the decimal number system. So for the decimal number system, we just when like the 1, 2 plus 3, 4, and the addition is performed, we just perform addition for each digit. And 2 plus 4 is 6, 1 plus 3 is 4. It's the same for the binary number. It's because it's the same number, right? So addition is very simple. For each digit, we can perform addition. And then first the last digit, the MSB is the sign bit for the two's complement number. So in this case, so we need to consider the signs of two operands. Fine. And then what is subtraction? Subtraction is actually addition, right? Because 7 minus 6 is the 7 plus minus 6. And then, which means then if we just change 6 to the negative number, then, and then if we just perform plus the addition for these two numbers, then this is subtraction. So actually add and subtraction is the same. That's why RISC-V has only add I instruction. Right? There is no sub I, because sub I is the add I minus immediate. Okay? So subtraction is also very simple. Okay? Then what is multiplication? So actually the multiplication is a little bit complex. It's a more complex than addition or subtraction. So and then as I mentioned from chapter 3, so we are learning about the hardware. So it means that we also need to consider the complexity or cost and performance of hardware. Okay? So until the chapter 2, we just learn about the instructions. Okay, and the performance we just handle the instruction count. Okay, but from the chapter 3, so we need to consider the hardware aspects. So it means performance, and it means the speed, latency, complexity, and cost. Multiplication. So I mentioned that addition or subtraction are simple, they're very simple. But how about the multiplication? It's more complex. Why? Actually, the multiply is more complex than the add or sum, right? So in real world, right? Why? 120 multiplied by 34. How can you calculate? It performs multiplication by 12 multiplied by 4 first, and then 48. And then we just performs multiplication. So 12 multiplied by 3, so 26. And we add the 48 and 36 is 408. That's how multiply is performed in real world. What can we observe? Actually, multiplication requires addition of multiple partial products. So these are called partial product. It's the multiplication. This operand is called multiplier. The multiplier number is multiplied by each digit of this is multiplicand. The multiplicand number is multiplied by each digit of multiply. Okay, and then partial products is generated, and then we need to perform addition for generated partial products. That's why multiplication is more complex than addition. Okay, let's see the multiplication hardware. So for the binary number, so actually each digit of a multiplier, so this is called the multiplier, and then this is the multiplicand, and then this is the final product. And then these are called the partial product, or PP, partial product. So actually, in order to generate the partial product, we need to perform multiplication for each digit of a multiplier, right? But the binary number, this multiplication is very simple, right? Multiplied by 1 is the same number. A multiplied 1 is the A. A multiplied by 0 is 0. Okay, so it means that it can be multiplicand or 0. So partial products can be multiplicand itself or 0. So what is different? Only the bit position is changing. Okay. So for the multiplication, and then so actually, so we are learning about the 32-bit computer. Okay. So which means that which data size is the 32-bit. So which means that if the more instruction is given to a processor, okay, then we need to perform the more RS1, RS2. But these numbers, these data are 32-bit data. So which means that 32 partial products will be generated. Okay. So actually it requires 32 addition, not 32. So we can just use the reduction tree, but usually, so theoretically, we can simply say, multiplier requires 32 adders. Okay. So and then this is the this slide shows the hardware of multiplication. When compared to the addition, so actually it's a little bit it's a bit more complex. Okay. And then you can also use the optimized version of the multiplier. But this is not a scope of this course. So actually this is the scope of the digital design course. Okay. Now we can also use the faster multiplier. Okay. Then RISC-V actually supports the multiplication instruction. Okay. So, but in order to use the multiplication instruction, we need to use the M extension. In lab number 2, we added the and extension in the compiler, right? So it means that the generated assembly instruction includes the more instruction. Okay, more is the multiply. But if the RS1 is the 32-bit, RS2 is the 32-bit, and then 32-bit data is multiplied by 32-bit data, then the result is the 64-bit, right? So the 32-bit data is multiplied by 32-bit data, then result is 64-bit, right? So actually, so when the multiply, so this file has the ball and ball H. So ball just stores the lower 64-bit to the RD, okay? And then ball H just stores the upper, this is 32-bit, upper 32-bit of the result, okay? And then how about the division? So actually the division is more complex than multiply. Divider is more complex than multiplier. So it is because, so when we learn about the division, that we firstly learn about the multiplication first, and then we learn about the division, right? The elementary school, right? Why? Also, division is more complex. It is because actually, so this is the example. So divided number is called the dividend, and then dividend number is dividend is divided by divisor. So when the division is performed, then we firstly check the upper part of the dividend, right? Then what is checked? Actually, for the decimal number, like the decimal number is 34 divided by 6. Then if we first check the first digit, 3 is less than 8, so it's actually 0. The quotient is 0. And then we check the 34 again, and then 34 is 30, and then 5 is here, and then remainder is calculated. Actually, it's the same. So what did I do? I checked the I compare the magnitude of part of divided and then division. So which means that division require firstly comparison, right? And then based on the result of comparison, then the quotient can be some number or 0. And then we need to check the next digit. So comparison and based on the result, and then something is generated, and then the result is changed. So actually, the division is takes longer time because we need to compare first, and then if else is required. Okay. So let's see this example. So this example, let me check the magnitude of 0, 1, 0, 0, and 1, 0, 0, 1. And then 1, 0, 0, 1 is bigger than 1, 0, 0. So the quotient becomes 1. Then you can get the remainder. Then for the next digit, it becomes 1, 0. Then it's smaller, 0, 0, and then finally we check the 1, 0, 1, 0 with the 1, 0, 0, 0. So the final remainder, then it's the final quotient. So because of this operation, the division is will take longer cycles. So actually the division is more complex. So RISC-V also supports the division and remainder instruction here. So also M extension is required. Okay. So this is the multiplication and division. So, and I'll stop here, I think, and then, as I announced I posted the announcement on Blackboard, and then the next class, we don't have anything else, but I will post the record is going to be, okay? Thank you for attention. See you in the next class. 감사합니다. 그 블랙보드에 그 시험이랑 그다음에 이제 다음 수업에 대한 공지 올렸습니다. 체크해주세요. So please check the blackboard for the next class and then midterm exam. Right?